I will start with a short introduction on RL and the contextual RL, and also I will explain a little bit of the related work in contextual reinforcement learning. Then I will present a generative view in contextual reinforcement learning, and I will further talk about how can we learn context variables that can help us in generalization in contextual reinforcement learning. And in the end, I will have a short discussion about how can we distinguish between causal and non-causal factors in the context variables. In reinforcement learning, as you may already know, we have a setting where an agent interacts with an environment through executing actions and receiving rewards and changing the world. And we already have seen most likely this famous graph that shows how this interaction is being done between the environment and agent, and how can we define a markup decision process that kind of summarizes this interaction. Reinforcement learning has a lot of different applications. One of perhaps important ones is that we can run a simulation, we can learn a policy in the simulation, and in some cases we can even deploy it in the real world scenarios into a robot or a system that interacts with the real world. In another aspect, in multi-agent reinforcement learning, different agents can collaborate with each other to solve a task. Further, in some other aspects, such as autonomous systems or self-driving cars, the agent actually is the car itself. By receiving some sensory data from the environment, it has to make decisions that suits the current state of the world that it's in. Particularly in all of these examples, what is important is that the surrounding world always changes, and eventually there are different settings, or as we call context in the world, that in which when they change, some parts of observations or the distribution of observations with them changes. For example, you can think of the context as different lighting conditioning. If our agent being a self-driving car and using an input video sequence as observation, if the lighting, for example, from the daytime to the nighttime changes, the agent still has to be able to generalize to the new lighting condition, although it might look completely different. Or perhaps if the car is going to cross a cross-section, depending on where the location of this cross-section is and how the system might be able to predict the behavior of the people that are walking by or the other cars, it might make a different kind of decision. So you can look at the context as a different location of a cross-section. In all of these settings, usually when the agent interacts with the environment, the change in the context might affect the distribution of the agent, and often the agents that are not ready to deal with this distribution change may fail to generalize. Also, a change in the context will also affect the credit assignment and the reward distribution in this interaction between the agent and the environment. And in the end, it might actually result in a different optimal policy that all depends on in which context the agent is interacting with the environment. So in this area, there is a body of work that tries to explain better this problem. One is a paper that introduces contextual optimization processes, which defines the context that the context space consists of k different possible contexts, and Within each episode, the environment chooses a certain context, and within this episode, the context is fixed. And further, based on this definition, they propose an agent that incorporates clustering of the observed trajectories into k different clusters. And then within each cluster, then the agent explores that specific context. And by applying some classification, it tries to identify in which context the agent is currently in, and then exploit that identified contextual model. Some limitations of this work could be perhaps that it is being explored in the low-dimensional spaces, and also only seems to be working under small or limited number of contexts. So in case of working with high-dimensional spaces or a large or unknown number of contexts, this work might have some limitations. Another work defines contextual decision processes as a generalization of MDPs and partially observable MDPs. And it defines actually the context as the observations and the history of the observations, and proposes a method in which in this setting can have a better generalization. However, this is only limited to contextual decision processes that have a small Bellman factorization rank. And in addition, it also poses several constraints, such as knowing the rank of the Bellman rank and some additional constraints that is required. Another more recent work is diversity all you need, and this work actually tries to use mutual information between the context, the current context, and the observation as a learning signal. And in addition, it uses the entropy of the policy across different contexts as an additional regularization. And by using these two, combination of these two, it tries to learn a policy that has a better exploration and is capable of adapting to the change of the context. However, it assumes that the context variable is known to the policy. Another work known as variational option discovery algorithm uses a variational autoencoder that first encodes the context into trajectories via the policy, and then actually decodes the trajectory back to the initial context. So using this kind of autoencoding behavior, it uses a probabilistic recurrent decoder that assigns probabilities or high probabilities to the trajectories that are coming from the current context. And this work also assumes a known context variable and uses this context variable as a supervised signal to train the decoder. In a slightly different direction, the Darla agent uses disentangled representation learning to not actually learn a context-related policy, but learn a disentangled state representation using the beta VAE. And this is done in a pre-training stage. And then by fixing the state representation, tries to learn a policy on this fixed state representation that has been disentangled already. With various experiments, they show that actually this method not only capable of learning well, but also it generalizes to unseen environments or environments with a slightly different settings. And they showed that learning disentangled variables helps in generalization. However, they don't particularly learn context variables, and they don't learn conditional policies based on different contexts. And in case of limited data, when we don't have enough data to learn a robust representation, this work might have some limitations. All right, so we looked at some recent work in the direction or the related directions to contextual reinforcement learning. Now I would like to talk about a generative view on contextual reinforcement learning. But before that, I will explain what I mean by a generative view and what is a generative process. So when I talk about generative process, I mean that we assume that the surrounding world, in the surrounding world or in the environment, everything is happening within a two-step generative process. And in the first step, we assume that a multivariate latent random variable Z is sampled from some distribution T of Z, where Z corresponds to a semantically meaningful factor of variation of the observations. So you can think of it as a higher level factors compared to the input space. And you can think of it as factors such as color or objects and so on. And in the second step, we actually sample the observations from a conditional distribution T of X given Z, X being the observation, and Z being this multivariate latent variable. We assume that actually the observation space has a higher dimensionality compared to the semantic space Z, which is actually can have some nice properties and capture some higher level concepts. And second, we assume that the data space can be explained with substantially lower dimensions that can be captured in this Z variable. For example, if our Z variable tells us the color is green and the object that we are looking for is cat, then after observing this latent variable and sampling from this conditional probability distribution, we can observe a sample in the data space, for example, in this case, images. Based on this generative view, we can define contextual reinforcement learning as having the environment of E of Z, which is receiving observation at time t and action at time t, and then further giving us the observation at time step t plus 1. So by defining in this setting, we can actually Z is again can be think of as a variable that is controlling some statistics in the environment or higher level concepts on the environment, such as shape, size of the object, and so on. And by changing this Z variable, actually the context in the environment changes. In the generative view for contextual reinforcement learning, the observations of an episode are generated from this generative model known as this environment E of Z in 3 steps. In the first step, a multivariate random variable C is being sampled from a distribution T of C, where C corresponds to a context. So the first step, we want to define in what context we are. In the second step, a multivariate random variable Z is sampled from a conditional distribution T of Z given C, where Z corresponds to the state of the environment and controls some statistic aspects of the environment, and defining how the environment is going to generate the next observations. And in the third step, the next observation is being generated using the environment. So by this definition, we can see that there is a connection between context and factors of variation. And further, we want to know how can we use actually context variables to learn or to train agents that can generalize better in the contextual setting. To have this a little bit more under control and evaluate some ideas in this direction, we use a simple reinforcement learning environment known as the grid world. Actually, it's a slightly different version of the grid world known as the contextual grid world. But the task is very simple. The agent is the triangle, and it can navigate the world. It can collect some objects known as goodies that provide positive reward, and it has to avoid some other objects or circles that are known as obstacles. And it has to, in the end, arrive at the goal, which in this case is this rectangle. The contextual aspect of this environment is that we always provide pairs of environments where every color in this pair are the same, but the colors of obstacles and goodies are flipped. And another factor that this contextual grid world environment has is that always the color of the goodie is the same as the color of the agent itself. All right. So for example, in the first environment in the pair, we see that the agent is yellow, therefore the goodie is yellow. But in the second pair, the yellow becomes the obstacle. So the agent has to kind of learn this association between different colors of itself and the object. So we would like to train agents, and we would like to also be able to evaluate the generalization in terms of goodie obstacle discrimination in the agent. And for that, we let the agent run in the environment within some certain number of episodes. And in the end, we count how many obstacles and how many goodies are remain after the termination. And we then count that. And what we would like to have is that we have 0 goals remain and the maximum obstacles, which in this case is 2, has remained. So the higher this goodie obstacle discrimination score is, the better the agent learns to discriminate between goodies and between the obstacles. And in addition, we also have a measure that counts how many times the agent reached the goal within a certain number of episodes that we evaluated the agent. To test how useful the context variables are, we train 2 agents. One is a normal agent that doesn't have any context variables. The second is a contextual agent where we provide the policy with a one-hot vector that represents the context that the agent is in. And we train the agent and then we evaluate it on the environment and different contexts. And in the left side, we see the cumulative reward, and we see that there is not much difference between the cumulative reward. However, by comparing the goodie obstacle discrimination, we can observe that the contextual agent performs significantly better in discriminating between goodies and obstacles. And this tells us actually if we were able to capture a good context variable, then we could change the behavior of our agent and push it towards a better behavior. But in this test, we only use the ground truth variable. And the next step is actually how can we learn these context variables. In order to achieve this, we already proposed a method called context adaptive reinforcement learning agent, or in short, CARLA, that incorporates a latent variable for the context into the policy and tries to learn conditional policy that are based on context variables. And there are 2 parts in the agent. One is the representation network, and one is the context network. And the goal of the context network is to learn a context variable. And the role of the representation network is to learn a representation that is useful to solve the task. And the policy then uses both of these representations, and it tries to learn a conditional policy based on the context variable. So if we go deeper and look at the context network, we can see that there are design uses disentangled representation learning as the first part of the context network, and on top, it uses a aggregating network that captures these disentangled representations and can also adapt them accordingly based on the gradient received by the reinforcement learning loss. And the first part is actually trained with elbow loss, which is and objectives that is related to VAEs, which I explain in the next slide. Having a look, comparing the graphical model of different methods and a variational autoencoder, I here compare, first of all, I have to say that the gray circles represent the observed variables and the white circles represent the latent variables. Comparing VAE with Darla, we can see that they have almost the same graphical model, but for example, Whaler or variational option discovery has a completely different trajectory where the trajectories are the latent variable and the context is the observed variable. While the Carla agent has two different parts. One is to learn a latent variable for the representation, and one is to learn disentangled representation for the factors of variation, and on top learn a context variable depending on the disentangled factors. Since we are using unsupervised learning techniques, particularly variational autoencoders to learn disentangled variables, we investigated a set of different techniques to learn disentangled variables using VAEs. And just to give a short recap about the VAEs, in variational autoencoders, we usually have two networks. One is the encoder encoding the input into a latent variable Z and doing the reparameterization, and the decoder taking the reparameterized variable and then trying to reconstruct the input. And in many of the VAE variants, there is a two-part loss. One is taking care of the reconstruction and trying to make the reconstruction as accurate as possible to the input, and the other is kind of responsible for compression and how much information we can keep from the input into the latent variable. And there are different formulations for the VAE and how the disentanglement can be done. And since we want to focus on disentanglement to kind of reverse the generative process and estimate Z or the factors of variation from the X, the input samples, we would like to have a look at different kinds of VAEs in this direction and see which one works best for our purpose. And particularly, we look into two models, vanilla VAE and beta VAE, where they have a fixed weight for this compression part of the objective in VAEs. We look at the annealed VAE that decreases the compression weight from the beginning to the end of training and tries to learn factors of variation one at a time. And we also look at a more recent work, such as Gecko, that tries to balance between these two in a dynamic way. So it can allow one go down or the other go down if required. In order to evaluate how much disentanglement we could achieve, we evaluate our VAEs with respect to the ground truth factors that we have in our environment using a beta VAE score. And in addition to the disentanglement evaluation, we also apply some context classification tests using Z, which is the output of the encoder, to see how much of the context information this representation has and which model actually provides the best. These are some examples of, on the left, reconstruction of different inputs via different variational autoencoder objectives that we use. And on the right-hand side is the comparison of beta VAE score. And we can see that the Gecko method, which had a dynamic technique to balance between the two loss, achieved the best disentanglement. And we can also see that the reconstruction examples are also considerably better than some of the other methods. And in the context classification test, we can also observe that the representation learned by the Gecko VAE achieves a better accuracy, both using a multilayer perceptron and a linear classifier. So these two tests shows us that Gecko seems to learn a useful representation that is able to capture context variables that are useful to learning a contextual policy. Now the next question is, how can we incorporate these context variables into the policy? One very simple way is that by having a state vector that comes from the representation network and having a context vector that comes from our context network, you can just simply concatenate these two vectors and pass it to the policy. There are also more advanced conditioning mechanisms that have been developed in certain areas, such as multimodal representation learning and generative models. Particularly, this work introduces film layer, where the conditioning vector or the context vector controls a bias term and a scaling term and can shift the input representation according to the context variable. In our work, we also compare these two mechanisms and see if we see a significant difference between the two. All right, so let's look at some results to test these different methods and compare it to some of the available methods. We used, of course, our contextual grid world environment, and we use an actor critic vanilla policy gradient with entropy regularization, and we train it on a number of 45 different context pairs that sum to 90 different contexts, and we evaluate them on 50 different episodes. Here are some of the results. On the left, we see the cumulative reward. In the center, we see the Goody obstacle discrimination, and on the right, we see the goal reach score. And first of all, we can observe that there is a significant difference between the performance of Darla and non-contextual to the performance of the Carla agent, and the Carla agent with different concatenation mechanisms actually outperform the other approaches. And it seems that actually using the Carla and the learned context variable and the conditioning mechanisms, we can even outperform the agent that used the ground truth variable as context. We can also compare different disentangled representation learning and how they affect the performance. Although we observe that Gecko VAE achieves a slightly better performance by tuning the beta in the beta VAE, we can also observe that the performance can be actually in a reasonable range. One of the drawbacks of the method that I presented also in Darla is that there is this offline pre-training stage that might be a little bit cumbersome in some applications or different tasks. And we would like to see in the next part if we can make our Carla online algorithm such that you run the agent and it starts to interact with the environment, and at the same time it learns the context network as well as the representation network at the same time. So it's just some modifications to make the Carla agent online. And this can be done using this algorithm that is available as in our paper. And comparing the performance, we can see actually that the online version of Carla can almost perform on par with the offline version, which is actually a good news that makes the Carla a computationally efficient method. All right, so we talked about context variables. We talked about how can we learn them, and we talked about how can we use them to learn conditional policies. But in this part of the discussion, I would like to talk a little bit about causal factors of the context variables. I would like to propose a hypothetical example where a causal agent and a non-causal agent are working on the contextual grid world environment. The difference between the causal and non-causal agent is that the causal agent is able to make the relation between the color of itself and the color of the goodie, and can discover that there is a causal relationship between the color of the goodie and the color of the agent. However, a non-causal agent only remembers this joint appearance of these variables and just memorizes them. If we hypothetically train these two agents on a set of training context pairs, both of them should be able to solve this task, and during the training, they could both manage to solve and achieve a good performance on the training context. However, if we provide these two agents with an unseen context, only a causal agent will be able to generalize and make this causal relation that it should look into its own color, pick the color, and look for an object with that color, and then move towards that. While the non-causal agent will fail to solve this task because in its memory or dictionary or whatever it learned, there is no association of these new colors and they do not exist. So this thought experiment actually tells us a little bit about the construction on the importance of learning causal factors of the context variables, and that finding the causal factors in contextual reinforcement learning is actually an important key for generalization. And if we have a mechanism in place that can allow our agent to distinguish between causal and non-causal factors and only focus on the causal factors, we may have a better chance in generalization to new contexts. In order to achieve this, what we would need is a mechanism that can allow us to disentangle different factors of variation. And from the previous part of the talk, we know that this can be achieved by using disentangled representation, such as those who can be done via variational autoencoders. And the next thing is to learn contextual policies that are based on these disentangled factors, which we already have discussed. How can we achieve this? However, we additionally need a mechanism that allows us to simulate interventions and allows us to agent to simulate different interventions and discover which factors are causal and which factors are non-causal. There might be different ways of doing designing such a mechanism, but one of the mechanisms that we worked on towards this goal is as follows. We use a pre-trained disentangled model, such as a pre-trained encoder, to extract some keys from the input space. So these features have been trained and have been fixed, and when the agent interacts with the environment, they encode the input representation into a prefixed disentangled space. And this can be treated as keys, which I will explain next what is the role of these keys. And in order to know what is in the environment, what is in the current environment, we use a state representation to learn some queries from the input space. And given these keys and queries, then we would like to calculate some similarities between these fixed factors that come from the disentangled space and these input features that come from the observation. And using this similarity map, or also known as the attention map, then we can copy some values from our input representation to the output, and this way we allow our agent to learn certain associations of different factors with each other. And on the top, then the output can be used to train a policy. In order to evaluate this, we train some agents on a number of 4 different context pairs or 8 contexts. And further, we evaluate them on 24 new context pairs or 48 contexts, where the colors have been seen during training, but all of these colors have been constructed into new combinations. So all of these 24 context pairs have only new combinations, and none of the combinations have been seen during training. So this kind of allows us to test the generalization, the causal generalization, if you will, from the training colors to the unseen context with seen colors. In another test, we evaluate the agent on 28 new context pairs where a new color has been used in the context. We use a proximal policy optimization algorithm that is known for having a good generalization and having a good exploration to solve this task. And we compare different modules, for example, the module that we propose, and we compare to similar techniques. Here are some results on the training context. And we can see the greedy obstacle discrimination score, and we can see that the different agents that we have tested, the non-contextual agent, the agent that uses self-attention, the Darla agent, the agent that uses concatenation or Carla, as well as our module known as the contextual attention module, all managed to solve the training context, as we also discussed in our hypothetical example. However, when we test these agents on these unseen contexts with the seen colors, we observe a significant performance degradation on all of the agents, while the contextual attention module performs slightly better. This also shows that actually having a mechanism that allows the agent to discover causal factors is an important aspect that state-of-the-art agents fail to generalize. And when we test all of these agents on completely new colors, we can observe that none of them actually manages to solve the environment up to a satisfactory level. And this can be explained by the lack of representation generalization and the fact that the representation kind of did not reflect what has been observed in the input space. All right. So we are coming to the end of the talk with a summary of today's talk. And we looked at different kinds of methods in contextual reinforcement learning. And we also saw that how knowing the context variable, either as a ground truth or a latent variable, can be helpful in generalization and also in the speed of learning. And we investigated different unsupervised approaches based on VAEs for learning context variables, and we studied how we can incorporate them into learning conditional policies. And we proposed a framework that allows us to do so to improve the generalization of the agent. And in the end, we had a look at the cases where non-causal agents fail to generalize to new context, and we kind of discuss how we can build agents that have a better generalization capability. All right, so now I will end my talk.